All right, so good afternoon. This is a short talk with a lot of slides, so I'll be going at about 6 slides per minute, seatbelts on. But I hope it at least intrigues you enough to read a series of papers in which we try to get computers to form linguistic theories. So some of this work came out in the last couple of years, some of it as early as 2011, but I'm not sure the linguistics community is aware of it. So a couple of words up front. We'd like to model comprehension, production, and learning. If we can model the production, then thanks to the rubber and bays, comprehension and learning turn into well-defined statistical problems. We just kind of get them for free if we can only manage the computation. Those of us who, in ACL, who are linguistically inclined, like to keep at least the bones of the classical linguistic representations, which are quite well motivated. But we also place probability distributions over those in order to allow comprehension and learning. And lately we've also been injecting neural nets to try to fit the data more closely. So Jacob talked about doing this for semantics, Chris talked about syntax, and I'll talk about phonology. So today's focus is basically on solving phonology problem sets. There's been a lot of work on recovering constraint rankings, but phonology is not just about recovering how a given underlying representation, or UR, surfaces in different contexts. It's also about a problem that's gotten a lot less computational attention, although Gaia has worked on it actually, which is recovering the UR itself. We need that in order to explain the surface variance that we observe. And I should mention that while I'm not paying homage to Chomsky 1957, it is the 50th anniversary of Chomsky and Halley 1968, which I'll basically be following the bones of that theory. So in order to probabilize that theory, what probability distributions do we need? And can we really do inference over lots of forms? And then I'll talk just a little bit at the end about trying to figure out which surface forms share underlying morphemes in the first place. First, I'm going to assume that that information is given to us. We just don't know the concrete morphs that express those morphemes underlyingly. So here's what a phonology exercise looks like. Here's a table of English verbs by inflections. And your job is to fill in the missing entries in this table. And I should point out this is very similar. It's actually exactly the same problem formally as another machine learning problem. Some users rated some movies, and you want to predict how they would rate other movies. That's also completing a table, matrix completion. And the way you solve this problem in that setting is to assign each user and each movie a latent vector in 3 space so that the user's rating of a movie, when it's known, is predicted by the inner product of those blue and red vectors. Okay, so a blue row vector times a red column vector gives a purple rating. And then you can take the same kind of inner products to predict these boldface entries that were left out before. So all we're doing is approximating the original partial matrix by a rank 3 matrix. So the product of this m by 3 blue matrix with this 3 by n red matrix. And that product is a m by n rank 3 matrix. So this is the graphical model that's being assumed here, is that we generate somehow a user vector and a movie vector, and then when we want to know how much that user likes the movie, we have this deterministic dot product. That doesn't always match the observation completely, so we put in a little bit of Gaussian noise, and we observe the result after adding that noise. It gives us some wiggle room. Okay, so let's take this and convert it back to phonology. It's going to be exactly the same in Chomsky and Halley, except that instead of using latent vectors, they used latent strings, red and blue strings. So what that's saying is that every purple string is the concatenation of a blue stem and a red suffix, both latent, and we just have to get those back. That seems pretty easy. You just have to partition all of these. Unfortunately, there's something called phonology, and then you could predict the missing forms by concatenating blue and red. So this is the model. Concatenate, but of course it's not that simple because there are forms that are not purely concatenative because the underlying forms change under contextual pressure. For example, S changes to Z, and sometimes we also have partial or complete irregularity, so the past tense of eat is not eated, it's ate. So that's not completely unlike the underlying form eat, but it's not totally the same either. So Instead of adding Gaussian noise, we pass this through some kind of phonological transduction, which in this case will turn S to Z. I'll give you another example here. This word resignation, underlyingly, we have resign. We need that G in there to get resignation. So we get resign and ation, and the vowels change and the stress shifts and we get resignation. If we'd put a different suffix on, we would have kept the vowels, but we would have lost the G, resigns. Okay, so here's a fragment of turning this into a graphical model. This is for English. Here's a little bit of our table. 2 by 2, resignation, resigns, damnation, and damns. And the labels of these, which are the row and column labels, so these underlying morphemes, are unknown variables in the graphical model. So ellipses are variables, and I've labeled them not with the name of the variable, but with a typical value. We observe these words, and the story is that the morphemes are concatenated into underlying words, which then go through some stochastic channel to give you the surface words. Okay, and of course the real model is much bigger than this. I'm just showing a little fragment, but if you think about this third person singular suffix, it's going to be connected to hundreds of words. So we're going to train the parameters of this using the expectation maximization algorithm, just like training a hidden markup model. So given some observed words, the E step is going to use our current model to guess where they came from, and that's the inference problem. So what's that doing? Well, we observe just these surface words down there, and then we try to fill in the rest. All the missing stuff. And then the M step is trying to train this editing process, this transduction, it's phonological grammar. That's easy if we have supervised data. It's just supervised learning of a log linear model or something. And the E step, harmonic grammar, and the E step basically gives us those data. So if the E step thinks that resigns came from resigans because of its global inference, because that G was needed over here for resignation, then the M step sees, oh, we deleted a G in this context, and it will try to set the parameters to make such a deletion probable in that context. So the idea is to make the children in the graphical model probable given their inferred parents, but we're trying to learn those stochastic phonological processes. We do that just by gradient ascent as usual. So there's another thing the M step has to do, which is to say that these underlying forms were also probable. So it may be that nouns, for example, tend to have stress on the first syllable, which is true in English, I think. It may be that roots in Arabic tend to be 3 consonants. So you'd like to learn stuff like that. And maybe most important, you'd like to learn that shorter strings are more probable than longer strings. As Bruce was saying yesterday, so that you don't just keep positing the same stuff over and over. If you could explain stuff predictably instead of predicting it, explain stuff by the phonology, which by reusing the same underlying form rather than having to posit a segment over and over in many underlying forms. Okay, so we try to make these probable as well. Okay, so I'm going to show you some results. We looked at 7 languages from different families, and these range, you'll notice, from tiny data to small data. So tiny data shows that we can generalize appropriately the way human linguists do when we see all of the relevant information. These experiments at the bottom are somewhat more realistic. There's some scaling up of inference here, and the data aren't as easy, and we have more forms missing at once in a way that's realistic. You're more likely to see forms that are more frequent in the language, similar to what Sharon just showed us. From a graphical model standpoint, these are actually big inference problems. So our evaluation setup is we just ask if we guess the surface forms correctly. Okay. So we ought to be, if we can get the underlying forms back, that should allow us to predict the surface form, just like when you're predicting if someone will like a movie. And we actually looked at 3 evaluation metrics. This isn't so important, but we asked, was the top probability prediction correct? In this case, it's not, because we predicted damnation instead of damnation. But according to this metric, we're still doing pretty well because even though damnation wasn't our highest probability answer, it still had a reasonably high probability. It's not negligible. And we're also doing reasonably well because the average edit distance weighted by probability to the correct answer is small. Okay. And we average these numbers over many training test splits. So we compared to a couple of things. One is if you don't really learn a phonology, so you learn that there's a certain amount of noise, the concatenations don't surface perfectly, but you don't learn what changes tend to happen and in what context. You just learn sort of the rate of noise. So that's sort of a lower bound. We hope to do better than that. And here's an upper bound. We hope to do almost as well as this, if somebody told us what the underlying representations are according to linguists, we still have to learn a phonology, but we don't have to get back the URs. Okay. So again, we're evaluating just the language learner, and we're evaluating how well the learner predicts held out words that the learner didn't see. We're not evaluating whether the theory is elegant, whether it does well according to Occam's razor. My elegance might be your inelegance, so I don't want to set myself up to deem what theories are elegant. Occam's razor is meant to give you more predictive theories, so the proof's in the pudding. Let's see if the theory actually is predictive. Good. So again, we're guessing, did we get this pronunciation right? So here's one of our graphs. This is fairly typical. If we see only 200 forms, so green is the noisy concatenation, that's still doing pretty well. It's only 1/5 of a character wrong on average. But it doesn't get any better as it sees more forms. Our method is the blue method, and you see as it sees more forms, we're getting the error rate down to about a 20th of a character on average, and we're catching up with how well we would do if we knew the underlying forms that linguists tell us. Okay, and the error bars here are average over 10 ways of splitting the forms that we saw and the forms that we didn't see. So here's a bunch of other graphs where the rows are the error metric and the column is the language. I'm sorry, these languages are so similar. This is the data set that we had. But here we have textbook exercises. And you see that for these 4 languages, our blue results are quite close to the red results that you'd get with an oracle, and quite far away from the green results. And our underlying forms do, if you're curious, agree reasonably well with what the linguists think. When they don't agree, it's either because there's more than one way to do the theory, or because you really can't unneutralize something if you haven't seen a particular form, and it's unreasonable to expect anybody to solve that exercise perfectly. Okay, so what did we just do? We are doing this sort of Bayesian thing where we have observed data, and there's this whole iceberg of unobserved stuff that we're trying to reconstruct. So the graphical model's generative story tells us which iceberg shapes are likely. We say that we're sampling from priors how this language behaves. So phi is the parameters of what underlying forms look like in this language. And theta is telling us what phonological changes are common in this language. And then we generate a lexicon of types. So this is going to be morphs and words. So for every abstract morpheme, we choose its concrete morph, so some sequence of segments. And then for every word, we say, okay, concatenate the morphemes, and then decide how it's going to come out. So sing plus ed, will that come out as singed, or singed, or sang? And so we pick one of those stochastically, and then whenever we actually need to talk, we just always use that form. So we're not using probability here to model token-to-token variation, which is one way that probabilities have been popular in the phonological community. We're using it to model our uncertainty about what the types look like. So this allows us to quantify the degree to which things are irregular, as in Chris Karoff's talk yesterday. And when we have these kind of smooth models that say every form is possible, but some are more probable than others, it's somewhat easier to learn because we can follow a gradient that tries to improve the probability of what we've seen. So again, this is orthogonal to modeling token-to-token variation, which we don't have in our data set, which is only types. So why didn't linguists do this kind of thing sooner? Well, the M step actually has been quite well studied, so learning the parameters of harmonic grammars. But that assumes that you already have the underlying form, and that's the job of the E-step. The E-step is actually pretty hard. So what we're trying to do is look at all ways of jointly filling in all these strings. Now, in principle, you could solve this by brute force enumeration of all the possibilities. At least you could do that if you only have finitely many possibilities. So then you have to limit the length of these strings. If you don't limit the length, the E-step is actually undecidable, fun fact. MCMC is a pretty general approach to inference in probabilistic models. It randomly walks around the space of reconstructions saying, well, here's my current guess for this UR, so what's a compatible guess for that UR? The problem is that this may mix slowly, and in a model like this, you actually get lock-in. So once you've chosen a way of, once you've decided that this will be the prefix, then that must be the suffix. So you can't change the suffix. And if you've got that suffix, you can't change that prefix. And so you don't move, or maybe you can move because of the noise in the phonology, but it's going to be fairly slow. Basically, the issue is we assume that concatenation is deterministic. These other methods that I'm showing here, so this is a series of papers that you could go read if you're curious, we've only worked out these other methods under a slightly restrictive assumption, which is that the probability of surface given underlying is a finite state machine. The reason we're doing that is so that we can exactly invert it, which gets us, given a surface representation, the posterior distribution over underlying forms, or the one best underlying form. But if you have that assumption, these other methods here can be faster or more exact. So these two methods, BP and EP, don't just say for each UR, here's my current guess. They say, here's my current distribution over all guesses. Here's my estimate of the posterior distribution for this underlying form. And given that, I can re-estimate the posterior distribution for that underlying form so that it's consistent. And I'll show you a little animation of BP later. So this allows us to keep updating our guesses in terms of each other. Now, dual decomposition isn't just an approximation. It actually gets back the single best configuration of these strings under the current parameters. I did tell you that that was undecidable, so you might expect that dual decomposition isn't guaranteed to terminate. It's not, but we find that it terminates in practice, and that allows us to do exact Viterbi EM because it gives us the Viterbi inference, which actually gave us our highest results, better than what I showed you before. Okay. So the idea in these machine learning methods is that the variables are sending each other messages to negotiate a consensus solution, and the way that they're communicating with each other is by passing around distributions or the parameters of distributions over strings. Okay. So a few questions you might have. Is this limited to stem plus suffix? No, a word could have any number of morphemes. So you can still draw that with a graphical model. Is it limited to concatenation? No, you can use multi-tape finite state transducers to do, say, non-concatenative morphology. This is a picture of Arabic. Is it limited to a single step of derivation? No, if you want cyclicity, you can stick an S on the end of resignations, and you get resignations using the same phonological rules and the same underlying forms. Okay. Is it limited to just doing strings? No, we had another paper where we're doing meaning vectors at the same time. So every word is represented as an embedding in meaning space, and it's an approximate sum of its parents plus Gaussian noise. This has exactly the same structure of the model. And you could do them at once. Okay, so what's wrong with this? So for technical reasons, we're using a phonological transduction model that's a little too weak. It's a probabilistic finite state transducer. It is the arcs out of a node are locally normalized, and that allows us to ensure that all the paths for a given input sum to 1, but we would prefer to globally normalize over those paths, which is what harmonic grammar is doing. Better yet, it would be nice, because they work very well, to give the distribution of surface given underlying using some neural net. The second issue is that we still have to tell it which morphemes are shared among words. We'd like to discover that, for example, from text. So we actually did try this in 2011 for inflectional morphology, where we weren't told which words, word tokens or types were in the same paradigm. We had to organize absorbed words into paradigms. That particular paper didn't use URs, but it could be modified pretty straightforwardly to do so. Instead, we were using, as in Chris's talk yesterday, amorphous morphology. Let's take a quick look at how that works. So here's a paradigm in German. And you can, in the model that we use here, any form can be, we can model its covariance with any other form. So the ways in which they influence each other. And you see here that this form Bracht is getting its vowel from one place and its ending from another place. So there's, just think about output constraints in OT. And the way we turn this into a probabilistic model is a Markov random field. So the goodness of some configuration among these strings, S1, S2, S3, S4, is a product of a lot of pairwise factors, each of which is computed by a finite state machine. So this is now an undirected graphical model. I was showing you a directed one before, which you probably want to use for derivational morphology, so you can continue to generate new forms ad infinitum. But when you have a fixed size paradigm, you can build an undirected model like this. So each of these potential functions is a globally normalized finite state transducer. And we ran belief propagation. Just quickly, this is what it looks like. So blue is telling red, I'm Breton, so I think you ought to be one of these things. I prefer some to others. And it's telling yellow, I think you should be one of these things. So red and yellow now each tell green, given what I am, I think this is what you should be. And now green is getting messages from 3 different places. And so its posterior distribution is going to be a consensus of all of those, in which Brachen is the one which satisfies all of the constraints best. Now, the way that these messages are being sent around, they're actually distributions over infinite sets of strings, so they're finite state machines, weighted finite state machines. So when we have this model, we need some way of getting the data we actually see, which is not any more type data, but token data. We don't see the paradigms. Actually, we see a few of them just because it helped us to seed the model. So the generative story is that the model generates data. And then, just as before, we're going to generate a lexicon of types, just as I showed you with the resignation stuff. But now we're going to go another step. We're going to use those types to generate text, using a simple unigram model almost. So we start out by generating our infinitely many lexemes, which are just abstract things. We use something called a stick-breaking process to get a distribution over a potentially infinite vocabulary. We'll only see a finite portion of it. And then each of these lexemes is going to have to populate its paradigm. It's going to need a distribution over the different forms in that paradigm, first, second, third person, singular, plural. It's got to choose jointly a bunch of forms that fit well together. And the distribution it uses for that is the graphical model that I just showed you. Okay, so it's parameterized by some parameters theta. And so we sample some different random words of German, but each of these paradigms looks like a real German paradigm. Okay. So it knows about the changes that show up. Okay, now that we've generated the types, we can generate the token. So here's a sequence of parts of speech. For each verb, I'm only showing you verbs here, we choose the lexeme, then we choose with an inflection of that lexeme, and then we realize it by looking up the surface form. Okay. So that's the generative story. So in order to do inference, so what I showed you before was wrapping belief propagation around dynamic programming, which is manipulating the finite state machines. Now we're going to take that and wrap all of that inside Gibbs sampling. Okay, so what Gibbs sampling is going to do for us is say for each of these words, we don't know how they're color-coded. We don't know the lexemes. So we observe the paradigms for a few words, and now that allows us to learn a little bit to get started about the phonology of German, the morphophonology of German. So now when we see a word Bricht, we see it can't be any of these forms. It doesn't match any of them, so it must have been looked up from some other paradigm. So this is the place that it's most likely to be because T is a good indicator of third person singular. Okay, so we put it there, and that immediately, through belief propagation, allows us to guess what the other forms of that paradigm might be. So when we see Breton, we know it probably goes in one of these two positions. We pick one randomly, first or third person plural. and we pop it in there. This word looks less likely to come from either the red or blue paradigm than to come from red or green paradigm than to come from some new blue paradigm. Again, probably third person singular. So we put it in there. And again, when we see Brecken, we could put it in one of two places. We decided to put it somewhere else. In the same place. So now we have two observations, third person plural Brecken. Now we can. That was the E step. And so now we can go back and do the M step using lots more paradigms that we've just organized the words into. And we keep on iterating this procedure, reanalyzing the forms that we've seen and recomputing the phonology. So that's basically the story. So that's all I really have to say technically, and I'll just close on a couple of words about future work. So even there, we still had to tell the system how many forms we had per paradigm. And so in future work, it would be really nice to learn the morphological structure of the language, which features are expressed in which syntactic contexts and why they're expressed, which morphological features are fused into morphemes. So one way to do this might be, instead of building a neural language model, maybe a syntactic model, over words, we could build them over underlying morphemes or underlying morphological features, and then say that the words that we observed went through a morphological channel that produced the fused things into bundles into morphemes, and then realize them as morphs, and then a phonological channel like the one that I showed you before that produces a string of letters or phonemes. Okay. So this is going to get harder and harder to do the computation for, but for those of you who don't go to ACL, now you know why everybody at ACL tries to bulk up on machine learning courses, because it allows us to do better modeling of the linguistics that some of us actually care about, and hopefully better science. Thanks.
We can take just one or two quick questions. Anyone has a burning question?
I'm at 27 minutes.
Excellent. Please state your name and affiliation.
Chris Dyer, DeepMind. So, Jason, you've been, using these, finite state machines since well before the neural revolution and things. And I know you're talking about various cool ways to neuralize these things. But one of the very interesting, I think, developments that we've seen in machine learning has been having explicit or independent inference networks that are based on neural networks that approximate posterior distributions in these complex graphical models.
Absolutely.
To kind of get rid of all of this interesting but difficult computational.
Yeah, so Brian Connerall, who's my collaborator on some of this work, has a paper with John Salak-Glassman and Chris Kirov that won an outstanding paper award at EACL. They wrote the paper without telling me, but they did exactly this. So they replaced the finite state machines here with neural nets, and they learned stochastic inverses to be able to train these, and then they did MCMC with simulated annealing. So that was in the paradigmatic case.
Right. So I asked this question because of that paper, and you were not on that paper.
Yeah, I cited it there.
So I mean, what do we make of this? Do we need FSTs, or should we be using neural nets now?
So the nice thing for me about the nice thing for me about FSTs, I guess, is that I worry that there might be that the proposal distributions from the neural nets might be bad. And maybe that's too much of a worry. So I'd like to be able to keep a hypothesis alive for several steps along the inference path, rather than completely ruling it out. There are other ways of doing that. For example, taking a mixture of a neural proposal with some noise distribution, so nothing gets completely pruned away, and you can resurrect hypotheses. So I'm really fairly agnostic about this. I think it's cute that the dynamic programming algorithms go through, but I'm not intellectually committed to them. That's really an engineering question.
All right, let's thank Jason again.